Okay, I think we're recording now. So I'm going to bring up, can everybody see the whiteboard okay? Just give a nod as long as it's up on the screen. Okay, good. So what we've got here are the acid-base buffer. This isn't buffer, this is titration. So that title, scratch that and put titration. But this is the problem we were working with yesterday, right? So it's a 50 milliliter solution of 0.25 molarity formic acid that was titrated with 0.25 molarity NaOH solution. Now, we answered some of these questions. I'm just going to go back over them because they're very important to address. We're not going to do the pH calculations because they take more time and we have a lot to cover today. All right, but when you're doing your titrations, you need to always make sure that you are paying attention to these first 2 points. And those points are, what is the initial amount of acid that's present? And what is the equivalence point going to be? You have to know when you hit equivalence because you have to change the mathematical equations you're going to use once you hit equivalence point. In other words, that's when you drop Henderson-Hasselbalch and you pick up new equations. So the initial moles, we found that what we needed to do was, it was, where am I here? Right, so 50 milliliters times the molarity, which was 0.250, and that would equal 0.0125 moles. So this is the total moles present of the formic acid that we're working with here. Okay, so this number is important. And then we're also going to find where is the equivalence point. Now, when we get into specific parts of the titration, it'll say X milliliters of sodium hydroxide was used. That value will become important in that specific calculation. But in general, we need to know when we're going to drop using the Henderson-Hasselbalch equation. So when is the equivalence point? Well, we have to find out. This is a 1-to-1 ratio. So we take the total moles that we calculated above. So this is the moles of acid. And we're going to be neutralizing that with the base, and the base is 1 liter over 0.250. This is just dividing by the molarity, the way that I'm setting this up. Okay, but I'm setting it up this way so that the moles cancel, because the equivalence point, we want to know what it is in liters or milliliters. And so 0.0500 liters, or you can call this 50 milliliters. Okay, so that means once any part of the problem says, what is the pH after 50 milliliters of NaOH or above has been added, that means that we've neutralized all the acid. Okay, so the examples we did yesterday, we found what the pH of the initial acid was. That used an ice equation, and we did the 5% rule. We found it was 2.17. And then we found the pH after adding 10 milliliters of NaOH, and we found that the pH would increase to 3.14. So if you're confused about those numbers, go back and look at the calculations that we went through yesterday in class. All right, so what we're going to do now, bringing us up to speed, this is what we want to look at today. What will the pH of the solution be after 50 milliliters of NaOH is added? So this is the key here. The equivalence point is at 50 milliliters. So now the question is, what is the pH, okay, at the equivalence point here? Now, keeping in mind formic acid is a weak acid and sodium hydroxide is a strong base, where should the pH lie? Above 7, below 7, right at 7? So we're just looking for a general answer here. Somebody speak up. Nobody knows?
Wouldn't it be above?
Yes, it would be above, okay? So most people, I would hope, know that at this point. So if you look at the sort of the PowerPoints that we went over at the beginning of class yesterday, there was a slide and it says strong acid and a strong base, the pH is equal to 7 at equivalence point. If you have a weak acid and a strong base, then the base is stronger than the acid that you're titrating it with. So you would expect that the pH at the equivalence point is going to be slightly above 7, okay? So yes, we should be looking for a value that's greater than 7 at this point, because this is our equivalence point, and it's sodium hydroxide, which is strong, with formic acid, and that is weak. So the question is, how do we deal with this? Because when we look at it, we can say that pH equals pKa plus the log of, in general, A minus, right, over HA. So in this case, HA would be formic acid and A minus would be the formate ion. So what you have to realize is at equivalence, this has been used up. The sodium hydroxide has chewed through all of that and delivered nothing but A minus in return. Okay. Now, you also want to keep in mind that because this sodium hydroxide is reacting with HA at equivalence point, there is also no hydroxide in solution, right? Every time I put some hydroxide in, it reacts with HA to give A minus. So at equivalence point, there's no hydroxide, there's no HA. Okay, well, if there's no formic acid or no weak acid concentration, that becomes 0. And if I have 0 in a denominator, I start to get errors. So I can no longer use the Henderson-Hasselbalch equation in a situation like this, right? Now, can I just start calculating the concentration of hydroxide to find POH and then go for pH? Well, I can sort of do that indirectly, but I can't just figure out, okay, how much hydroxide is present based on the amount added, because none of it is left in the solution, right? So the only thing that's really hanging out in solution at this point is A minus, which is a weak base. So I'm going to need to figure out how I can represent A minus and turn that into pH. And I obviously cannot use the Henderson-Hasselbalch equation to do that. So what I'm going to do is turn around and find, for a starter, the moles of, this is A minus, but I'm writing out what it actually is for this case, the formate ion. How many moles of formate ion do we have at the equivalence point? Okay, so this is actually a very easy number to grab. Does anybody know where we would find it?
Didn't we already solve for it?
In what manner? We did technically, but we didn't call it that. Where would I find the number? Okay, so
The same as the NaOH reactant.
So we're on the right track with the NaOH reacted, right? But how much, where do you officially grab it from? What's creating A minus? The dissociation of what? Okay, so HA.
Dissociation of the acid?
Exactly. The acid, when it reacts with the hydroxide, so yes, to the hydroxide, when we said how much hydroxide has been utilized. If we look at the acid, right, or the hydroxide at equivalence point, that is what's creating A minus. So if HA to A minus is going to be a 1-to-1 ratio, then when I've used up all of the HA that was present, that must be the amount of A minus present. So at equivalence point only, the amount of the formate ion is equal to the initial amount of the formic acid. So it's going to be 0.0125 moles, okay? So we know that. So now the question is, can I somehow start utilizing this to find a concentration? Because if I can find a concentration, then I might be able to work it into an ice chart if I work the backwards equation. Right? So you'll see what I'm talking about in a minute here. So let's see if I can find the concentration so that when I set up ice, I have something to put into that initial slot for the ICE. Okay, so now the question is, I know the moles. Can I find a concentration of the formate ion? So I should be able to do that fairly easily, because concentration, molarity is moles, well, we just determined that, over liters. Now the question is, what is the liters here? Where do I get that value?
The 50 milliliters of NaOH and Whatever you started with.
Exactly. Okay. So I started with 50 milliliters of the formic acid. None of it had converted into formate, right? So 50 milliliters, which I'm writing out as liters here, plus another 50 because there was 50 milliliters of NaOH added. So I need to sum those up to get 0.1 down there, okay? And then complete this, and I can find that the concentration of the formate ion in solution at equivalence point is 0.125 molarity. Okay. Everybody okay with how we got to this point so far? All right. So what I'm going to do here is, give me 1 second because I am going to clear the board so that we have a little more room to work. Okay. And let's keep that concentration in mind, 0.125. So you want to have that marked down. Okay, so now what I can do is I can look at the actual equation and set up an ice chart for this. Now I want this to return either hydronium or hydroxide. Now it's going to be difficult to get hydronium back because I'm working only, all I have is A minus, right? So I have to work with that concentration, the formate ion. So what I can do is I can say the formate ion is going to be in the presence of water. Now I'm going to leave water out because it's not part of our equilibrium equation, right? It could be in equilibrium with its conjugate acid, okay, if it was able to take a proton from water. So this will be aqueous. And then if this took a proton from water, then water would become hydroxide. So what I can do is I can find hydroxide content, which means I could then find pH because hydroxide can give me POH and I can use KW to find pH at that point. All right, so what I want to do here is now I would use an ice chart. Okay, because the question is how much hydroxide is present in solution. Well, none of it is present directly from the actual hydroxide titration. That's all reacted with HA. So we need to find it based on this equilibrium, okay? And we're gonna need to find the KB because this is no longer an acid over here, right? We're doing this for a base. So what we would do for the ice is we would say 0.125 because that's the concentration at the equivalence point here. Okay, and this would be 0, and this would be 0. Right? And then we allow it to go and react. So this is going to be minus x plus x plus x. And so at equilibrium, we're going to have 0.125 minus x, x, and x. All right, so we don't have KB. That wasn't given to us here. But what do we have? If you're going back through your notes, I haven't specifically put it up today. So last time I did give what value? The Ka. All right, so if we have the Ka and we're dealing with conjugates, then we can find the Kb. So we do have the Ka for formic acid. So that means I can find the Kb of the formate ion by using Kw. So what you would do, okay, and I'm going to try to save a little bit of space here, you're going to take Kw, 1 times 10 to the negative 14th, divided by 1.8 times 10 to the negative 4th. That was the Ka I gave yesterday. And that is going to equal 5.6 times 10 to the minus 11th. So Kb for the formate ion is going to be 5.6 times 10 to the minus 11th. Now that's important because I'm going to set this equation equal to that. So I'm going to say 5.6 times 10 to the minus 11th is going to be equal to x squared over 0.125 minus x. Okay. Now, you can try quadratic, but because of time and because this is really the way you should be executing this on exams to save yourself time, we do the 5% rule. So we're going to drop this and assume that it's small enough. So I would take 5.6 times 10 to the minus 11th multiply that by 0.125, and then take the square root. And that's going to tell me that x is going to be equal to, just change my page of notes here, 2.6 times 10 to the negative 6. Okay, so if this is x, x represents at equilibrium the hydroxide content. Okay, so if I take the negative log of this value right here, what do I get? If I take the
POH.
negative log, go ahead.
The POH.
Exactly, right? I can get the POH from that. So I can take negative log 2.6 times 10 to the negative 6. And if I do that, I'm going to end up with the POH value. And that turns out to be 5.59. Now don't stop here, because the question was not what is the POH at equilibrium. If we go back up, the question said what will the pH of the solution be at the equivalence point. So we're pretty much there. The last thing we would need to do is use the KW conversion, and we would say 14 minus 5.59 is equal to 8.41. This is the pH at the equivalence point. And if we go all the way back to what we said before we even started any math, we said the equivalence point pH should be slightly basic. It should be above 7 because we're dealing with a strong base. And sure enough, it's not sky high, but it is slightly above 7 on the pH scale. Okay. Any questions regarding how we solve this? All right, so when you have a weak acid and a strong base in this scenario, this is only for equivalence point. You need to set up the reverse equation with the conjugate base, find Kb, and you need to go through an ice chart. Now you have to have that initial molarity. So the first part was us finding the 0.125. You have to have a value to put in there in order to make this work. Okay. All right. So post equivalence point, when we're doing this titration, now we go to 55 milliliters. Okay. So the question becomes, what will the pH of the solution be after 55 milliliters of NaOH is added? So now let's take a second and just think, before we start doing math, qualitatively speaking, what is in solution? Do I have any of the formic acid in solution here? Do I have any HA, formic acid? Somebody should have answered this by now. This is a very low-hanging fruit question. Do I have any acid left by now? Okay, the answer is a resounding no. What did we just finish calculating? The equivalence point, where we've used all the acid up. Am I going to generate more acid by throwing extra sodium hydroxide into the solution? No. Okay, yeah. Immediately, that should be a no. Anytime you're past the equivalence point, the HA, whatever weak acid you have, has dried up. There's no more of it. Okay, so now, do I have any hydroxide content due to the sodium hydroxide in solution? Good, now I'm seeing people starting to nod yes. Yeah, that is a absolute yes, because at equivalence, all of the sodium hydroxide has reacted with the formic acid. But now I've gone 5 milliliters past any formic acid that was left in solution. All this is doing is hyper-concentrating the base into the solution by adding hydroxide with no acid to react with, all right, unless you want to consider water and acid in that case. So do I have the formate ion in solution? Do I have A- in solution?
Yes.
Yes, yeah, that didn't go anywhere, right? So adding base to another base is not going to react with that base, right? The acid's gone, the A- has been generated. So what I really have in solution here is I have some hydroxide, a considerable amount now, because I've been titrating sodium hydroxide in with no acid to react with, okay? And I also have the presence of my formate ion as well. Okay. So what this could end up creating is a complicated ice chart where I need to know the concentration of this, and I need to know the concentration of this, because if you go back up and look at the equation, instead of this being 0 now, I would plug another concentration in there. Okay, now you've seen some of this in the lab material as you've been going through the lab. Okay, because especially this current lab that we're working with, if you're doing a diprotic, you're carrying certain values from one ice chart into another one, because when you start at that next initial point, it's not 0 for everything. But there's something we can use our logic with here, okay, in order to overcome this. And the reason that we can make this easier is that this is extremely strong, okay? And relatively speaking, that's supposed to be an O there. This is going to be extremely weak in comparison, all right? So if I start to look at the pH or the POH at this point, what is going to be the dominating or contributing factor to the POH at this point? The hydroxide or the formate?
The formate?
Okay, so anybody agree with that, formate? So it should be the hydroxide, right? Now, why is that the case? Because hydroxide is strong compared to formate. So formate, here's the reaction for the formate up here. What we're saying is formate can react with water, which we didn't show here from the equilibrium, to generate some hydroxide content. Do you think it's going to be able to do that to an appreciable extent? Look at the Kb for this reaction, 10 to the negative 11th. Is that a large or a small number?
Small.
Very small.
Very small.
Very small, yeah. So what that means, okay, and this is all important when we get to these quiz questions, you have to be able to understand this logic. What that means, if this number is extremely small, hydroxide is found in the numerator. So if this is a very small number, that means these X values are very small, right? Because Kb is very small. So that means there is very little hydroxide that can be generated by formate because it is such a weak base. Its Kb is 10 to the minus 11th, right? Sodium hydroxide doesn't even have a Kb because it goes all the way to the right. It just completely dissociates and releases all hydroxide content available to it. So far and away, if I have good tabs on this, that's all I need to know. This is going to be almost like the 5% rule. This is going to be insignificant in its contribution to the hydroxide content in the presence of sodium hydroxide, which is now going to be present in the solution. Okay, so what I need to focus on now is hydroxide concentration. Now, what's nice about this is that if I find hydroxide concentration, I can directly hop over to POH and then pH. So I will not need what in this case. Does anybody know? I'm not going to need to set up what.
An ice chart.
That's
Ice
correct.
chart.
Exactly. Okay. You will not need an ice chart in a situation. Now, these are the points I'm trying to make. This is very important. You up through all the volume you added to the equivalence point, you use Henderson-Hasselbalch. Then at equivalence point, we need an ice chart. Then after equivalence point, we don't need an ice chart. So the only time we needed an ice chart was to find initial pH and to find pH at equivalence point. Those are two distinct points. Everything in between does not need an ice chart. I want you all to focus on the fact that we are not always using ice charts. This is very important, okay? Because there's been an overwhelming number of people, and I seriously feel bad about it. When I'm grading, I see them going through all of this effort to set up ice charts when all they needed to do was put concentrations into Henderson-Hasselbalch, or all they needed to do is calculate a PKB or something of that nature. Okay, so please, if it's confusing, stay behind, talk with me at an office hour, or email me for a separate private office hour, but make sure you know when to implement these and when not to, because they do chew up a lot of time if you don't need it. All right, so hydroxide content, getting back to this. All right, the question is, where do we find the moles of hydroxide, right? So we're going to need two things. We're going to need the moles of hydroxide, and we're going to need the liters that it came over with, all right? So the liters is probably pretty easy to answer if we knew how to answer it for the equivalence point. Where am I going to find the liters? It's going to be the initial volume of the acid, because that, while the acid's not there, the volume that it took up, the aqueous volume it took up, is still there. And we started with 50 of that. And now instead of 50 milliliters of hydroxide added, we've added 55, right? So in the past equation, I'm just going to hop back up so people can see. Actually, we've already deleted that part. Never mind. All right, but before, this 55 here was a 50 at equivalence point. Now it's 55 because we've added some additional. So what we're really keeping track of here is the total volume that the hydroxide is hanging out in. Now here's the next question. Where do I find moles? How do I get moles of hydroxide? I've titrated 55 milliliters of it, and I do know that the concentration is 0.250 molarity. So can I just take this times 55 milliliters, or 0.055 liters, and find the total amount of hydroxide in solution?
You need to add that to what's already in the solution.
So yeah, you're on the right track with that. Here's the key, all right? 50 milliliters of the hydroxide was used for what?
To neutralize the acid.
Exactly, to get rid of the formic acid, right? Can I account for that sitting in solution? Do I have 50 milliliters worth of sodium hydroxide sitting around as moles? No, right? That's been used up in the reaction. So how much do I really have? Right? 5 milliliters of sodium hydroxide has been added above and beyond the equivalence point. That is the amount that when it hit the solution did not react with acid, has completely dissociated into hydroxide content, and is therefore valid in this equation, right? Because we want to check the pH at this direct point. So what we would do is we would take this times, instead of 55, it would just be 5 milliliters, right? Which I'm converting into liters because of molarity. So looking at the fact that I have 2 sig figs here from the 5, my answer will have 2 sig figs. And if you calculate that and round, you're going to get 0.0013. Okay? And that is moles of sodium hydroxide that's currently sitting inside of the flask we're titrating. All right, so now what I can do is I can take this value. All right, so I'm going to rewrite this down here now that we have numbers to work with. The hydroxide content is going to be equal to 0.0013 moles of hydroxide over 0.0500 plus 0.0550, right? So these are the 2 milliliter volumes that we've calculated into liters. So you put all of that into your calculator, and what you end up with is 0.012 rounded approximately. This is the concentration of the hydroxide ion. All right, so now what do I need to do with that?
Take the negative log and then find POH.
There we go, right on track, okay? Negative log of 0.012. There are 2 significant figures in that value, so I should go 2 decimal places out on my POH, and we find that POH is equal to 1.92. Okay, so this is the POH. I go 14 minus POH. That will give me the pH, and I find that the pH is 12.08. Does that make sense? It should, because what's happening is at equivalence point, we're at this fragile tipping point, right? So we've got 8.41 as the pH, but there's no acid left. So once I pass that point, every drop of sodium hydroxide that I add is skyrocketing the base content in the solution without any acid to react with. And that's why we see just over the course of 5 milliliters, there's a huge climb in the pH up to the region of about 12. All right, and this would apply for anything past this math. So I picked out an example where I said 5 milliliters because it's 55, but I could say 60, 65, 70. It's the same concept. You would just need to know how many milliliters of NaOH you are past the equivalence point, because that's going to change the moles and the volume of NaOH that is sitting in solution. All right, and that's titration math. So I will open it up to questions for a minute or two, but I want to keep going. And remember that I am recording this session to put on YouTube. So if you have personal questions, I would hold off till the end of class when I finish the recording, just so I don't have to edit that out or you don't appear asking that on YouTube for the rest of the class. Any questions?
So in the lab for the equivalence points, like for part, I guess, D and E and like the calculations, is that how we would do it? We would like use the volume, like point, like the 5 milliliters, like that you
Are
use?
you talking about for the titration part 2 lab?
Yes.
You'd have to look, I believe. So the thing with that lab is that you have multiple equivalence points.
Mhm.
So before you're doing this, you need to make sure that you've gone through both the equivalence points before you would be applying this type of math. Okay, and I don't remember offhand the volumes and equivalence points that are shown there. And I can help look at that at a later point if you want. But in general, when you have, so the point of lab 2 is that it's a diprotic acid. So you're going to hearken back to the math that we did last week when I was showing the diprotic acid. And I said, okay, we have Ka1, we go through all this, and then here's Ka2, and we have to bring things down from the ice chart in Ka1 and plug them in for Ka2. So as you get down further and further, because as we go A, B, C, D, E, you're adding more base, which means you've gone past the first equivalence point and you're headed towards the second one. So I believe the math in that case, most of what you're going to be doing is dragging your values from the previous setups and putting them in as the new initials with a little bit of math there, and then solving those ice charts based on that. Okay. All right. So what I'm going to do then, I'm going to minimize this board. Probably actually should delete some so I have some room to work. And then we're going to head over into the quiz and take a detailed look at that. And that will probably bring us pretty close to the time for our class, because we're at about 1:10 right now. Okay, so I would encourage you, as you're continuing to take notes, if you have the ability to, pull up the quiz in Canvas. I'm going to be showing it here on the screen share, but you want to make sure that you are able to follow along well enough. Okay, so let's take a look here. Okay, question 1. The Ka of any acid summed with the Kb of any base will always equal Kw in return. This is false. So this will only apply when you have a conjugate pair that you are working with. So it is true anytime that I'm dealing with, for instance, the two values going into the Henderson-Hasselbalch equation, because that's HA and A minus. It will be true anytime I have a conjugate pair of any sort, but I cannot just mix and match. I cannot take acetic acid and the Kb of ammonia and add them together and expect to get Kw back. For acetic acid, it has to be the acetate ion, and for ammonia, it has to be the ammonium or the salt version of that conjugate base. I can't, or conjugate acid. I can't just put anything in there. Okay. Question 2. So this is where we started. There were 3 questions that required more detailed math, and this is where some people did okay, other people didn't do okay. But we're going to take a more detailed look at some of these. So use the Henderson-Hasselbalch equation. I'm going to stop right there. The number of people that didn't even have the Henderson-Hasselbalch equation present in their work was astounding. It says in the instructions, use the Henderson-Hasselbalch equation. Now, some people set up an ice chart, which was not needed, and then after they obtained values, they put that into the Henderson-Hasselbalch equation. But some people just went through the ice chart, and you can solve this through an ice chart and get the correct value, but it was not needed. And that's where I think a lot of people started to say, you know, I didn't feel I had enough time, because you were making far more work for yourself than needed to be here, right? So you've got a buffer solution. It's got 0.5 molarity NH3, which is a base, and 0.2 molarity NH4Cl, which is the conjugate acid. It's in a salt form of that base, okay? And then the pKb for ammonia is 4.75. So there's two ways that you can solve it. I'm going to show you the way that I intended. All right, I'm not going through any of the ice chart ways, because that is far more complicated than what needs to be done here. But I will show, there were a couple people that were either, they got it correct using the pKb, or they were partially correct and they need to understand where they went wrong. All right, so we're going to take a look at both here. Okay, so minimizing this, what we are going to do now is take a look at the solution. So for this problem, the way that I intended for it to work was, you say, all right, it tells me use the Henderson-Hasselbalch equation. So I'm just going to write that. pH equals pKa, okay, plus the log. And I'm going to put the actual values in here, not just the generic. Okay, so it's A minus, which is representative of a base. Okay. And an acid, the acid in this case would be the conjugate acid, which is NH4Cl. Okay, so there we go. Now, when you get ready to do this, you have a pKa value that's required for Henderson-Hasselbalch. So because I gave you pKb and these are conjugates of one another, you can just turn around and say 14 minus 9.25. I'm sorry, jumping ahead of myself there. Minus 4.75 is equal to 9.25. Okay, so that's the pKa. So the goal was you grab the pKa to plug in here. The concentration's already given in the problem, so we're done. Okay, I finished this in, I don't know, 3 minutes with explaining it in more detail and pausing to, you know, mention things. So all you had to do was take 9.25 plus the log of, now the concentrations I'm just going to tell you, but they were back in that equation. Okay, the concentration for the base for the NH3 was 0.5. So you would have put that up here. And then the concentration for the conjugate acid was 0.2. You put that into your calculator, you find that the pH, it was equal to 9.65. Out of the 3 problems that had to be worked, this was the one that the class was most successful with, right? But there were still some people that were having issues here. So that's it. No ice charts. You should have just grabbed those values, done a pKb to pKa conversion, and you're good to go. All right. So I'm telling you, I'm giving you fair warning right now. I absolutely will be putting these types of problems back on the test to test you and make sure that A, you've learned how to execute these problems, but B, you need to realize I have a limited number of problems I can choose from. And I'm going to give you some that require a lot of math, like diprotic acid ice charts, okay? But you should not, if you're going through your test and you realize you're filling out your 7th ice chart out of 13 problems, you're doing something wrong, because that's way too much problem solving for that amount of time period, okay? So that's all you had to do here. Now, I am going to just show people, because everybody has different methods, and one of the things that's very true is that there are a lot of different ways we can approach this. There's a lot of relationships that acids and bases share with one another. So some people were taking the pKb and plugging it into the Henderson-Hasselbalch equation. They didn't solve for a pKa. You cannot do that and keep the Henderson-Hasselbalch equation as it is. It won't work that way. However, there is an alternate version of the Henderson-Hasselbalch equation. Okay, now, this was not directly taught in class, but if you use your logic or you've seen it elsewhere, okay, then you're welcome to use it. So the POH can be equated to the PKB, all right? But you have to be careful here because it is plus the log. And what do you think is going to happen to the log in this case? It's going to be what's on top. Since everything's flipping, the conjugate acid now goes on top instead of the base. Okay? It's going to be conjugate acid over the base. So you have to keep in mind, the original Henderson-Hasselbalch is dealing with an acid. pKa is a derivative of Ka, and then it looks at HA over A minus. This is looking at the base, right? And then the conjugate acid of that base, however you want to represent it, B and BH plus on the top. So when you do this, it means the values would be switched here. So you can turn around, if this is the way you wanted to solve this equation, and say, all right, I don't want to do my conversion for the pKa, so I'm just going to put pKb in here because that's what was given in the problem, plus the log. Now you have to remember to reverse these. It's the conjugate acid over the base. So it's going to be the opposite of what we saw above. It'll be 0.20 over 0.50. Okay, that will equal the POH. So if you solve for that, you're going to find that the POH is equal to 4.35. And then that is not the answer because it wants you to find the pH. So you still have to do a conversion using 14 minus 4.35. Okay. And if you do that, you end up with 9.65, the same as you did right up here. So it is acceptable to use either method. My original intention was you do one pKa conversion, you plug it into Henderson-Hasselbalch with the concentrations already given, and you have your pH. All right. So going back to the quiz, that's question 2. Okay, question 3, out of the multiple choice questions, I would say this and 4 also had a decent number wrong. This was supposed to be a free point. And I was a little upset that there was a large number of people that were either taking wild guesses or didn't know how this worked, okay? This is the titration of a weak acid with a strong base. Based on the titration curve, which of the following is the most reasonable value for the weak acid? Okay, for its pKa value. So you've got a couple of choices down here. Where is the equivalence point? 20 milliliters.
20.
So if you go up, you can see the equivalence point smack in the middle there. We've already done labs about this. We've talked about it in lecture. The equivalence point is sitting right at 20. So half the equivalence volume for a weak acid strong base titration is the pKa. The pH will be equal to the pKa. So if you remember, we've looked at log, and then when those values are equal, it becomes log of 1. That drops out to 0, and the pH equals the pKa. So all you had to do is come over to 10, which is the half equivalence volume, and then estimate. And I made it very clear. I didn't put it a bunch of values that were kind of close together. So 10, if you come here, here's 4 on the pH, and it looks like it's just slightly above that. Now the next line is 6. So halfway between these two would be 5. It's not quite that. Okay, so we're going to say it's 4 point something. Well, there's only one answer that's 4 point something. So it's definitely not 5.7 because it's not even halfway in between 4 and 6. 4.5 is reasonable. 9 is not reasonable. That's up past the equivalence point. Okay, and then 3.8 is too low because we're definitely at 10 milliliters. We are definitely above that line. Okay. That's the only thing you had to do to solve this was just look at the equivalence point, then take half the volume of the equivalence point and see where the pH was because pH equals pKa at half equivalence point. Okay, question 4. This was a reiteration of the one from the previous quiz, and there was still an overwhelming number of people that got this wrong. So let's talk about this. Right? A given base has a pKb of 2.85. Which of the following statements would be true of its conjugate acid, HA? Right, now, we'll save all of the above are correct. If we can get at least 2 of these to match up, then we'll pick that. All right, so I see the acid would be strong given the base is weak. We'll come back to that. The acid would produce very small amounts of hydronium ions. We'll come back to that. The acid would have a pKa between 10 and 11. That's easy to find out because I already have a pKb. So if I have a pKb, all I have to do is take 14 minus 2.85 and I've got the pKa. Right? So if I do that, the pKa is 11.15. That's greater than 11, so it doesn't fall in that region. That gets rid of, the acid would be a pKa between 10 and 11. That also gets rid of all of the above answers are correct. So we're down to 50-50 at this point. All right. Now, we have to start using the logic after this, okay? The pKa of the conjugate is 11.15. The pKb is 2.85. What does that say as far as the relative strength of the conjugate acid and its base?
The acid is very weak compared to the base.
That is correct. All right. Now you have to remember we're in the P scale. That means that it flips from the Ka and the Kb scale. When you convert into pKa and pKb, smaller numbers mean stronger. Just like pH, a smaller number means a stronger pH or more hydronium present. So if the pKb is 2.85 and the pKa is 11.15, that means that the base is stronger than the acid. So saying the acid would be strong given this base is weak is the complete antithesis of what's going on here. It's a total opposite, right? This is a much stronger base than it is a conjugate acid. So that's out. So the correct answer is the acid would produce very small amounts of hydronium ions. Now this, we should be able to deduce based on everything else. Why is that the case? Because what did we just say about this acid? It's weak, right? So if an acid is incredibly weak, all right, then that means it has a very low ability to produce hydronium ions. It's not going to dissociate very well, meaning it's not going to give off a lot of acidity. Okay, so the correct answer here would be the acid would produce very small amounts of hydronium ions. All right, question 5. You're asked to develop a buffer system to buffer a solution with a pH of 4.25. Right, so they're giving a pH value. We're not going to be solving for that here. The only acid available is formic acid, which has a pKa value of 3.74. With this information, find the ratio of sodium formate, the conjugate base, to formic acid required to make a successful buffer. Okay? There was a large amount of the class that said 1-to-1 and moved on with almost no math. Right? At 1-to-1, the log function drops out and the pKa equals the pH. 4.25 does not equal 3.74, at least not the last time I checked, right? So that means 1-to-1 is not an appropriate answer here. If I was having an equal amount, okay, of the conjugate base to the acid, I would not end up with this. The pH and the pKa would be the same value. All right, now what you need to do is use Henderson-Hasselbalch and solve for that ratio. That's all you have to do. No ice charts, nothing else like that. So let's take a look at this. All right. So for this problem, the way that you want to start approaching it is you would say, all right, the pH is 4.25. So I'm going to put that over and set that equal to my Henderson-Hasselbalch equation. The pKa is 3.74. And it wants to know what the ratio of conjugates should be. A minus, okay, and HA. So this is the formate and the formic acid. So what I need to do is solve for this. I don't need to solve for the log of it. I need to solve for this itself that I circled. That is a ratio right there. Okay. Now, some people were able to get through this first part and then they didn't know what to do with the second part. Some people were setting up ice charts. Some people just said 1-to-1 and moved on, maybe because they felt stressed with the time. Again, this was meant to be relatively quick. So what you did was you took 4.25 and you had to get rid of 3.74, because if we want to find the ratio, we have to isolate it by itself, right? Just basic algebra here. So that's going to give us 0.51 equals the log. Okay. Now there were a couple people that had 0.51 as their answer. Now the problem with that, having 0.51 as your answer, is that 0.51 equals the log of the ratio. It doesn't equal the ratio itself. So how do we get rid of a log? We take the anti-log. Now here's where a lot of other people had issues. They put to the negative 0.51, okay? When we take 10 to the negative value, it's because we're coming out of a p-based system. So whenever there's a negative value up here, we're doing that because we originally took the negative log to begin with. So we have to put a negative value back in to get out of the p system, right? Here, this is just the log of the ratio, right? We're not taking the log of a pH, we're not taking the log of a pKa or anything of that nature. It's just the log of some concentrations. So that means to get out of regular log, not a negative log, I have to take 10 to the 0.51, right? Now I did give partial credit if you came up to this step and then you put negative here. So I believe with negative, it came out to like 0.3 or something like that, which there were quite a number of people that had that. And I understand why. I tried to only take off, I think, half a point or a point if that was the case, all right? But the way that this should end up is that when you finish this, it should be 3.24 is the ratio that you would need of conjugate acid to base, okay? So varying degrees, again, some people it was very obvious it was a guess. Some people at least knew to condense this, but then they set it to 0.5 and put that as the answer. You got to get rid of the log in order to get the ratio, okay? And then if people had it mostly correct, it was usually because of this. There were quite a number of people that ended up taking the negative. Again, I understand why, because we've been doing that a lot, and it's easy as you're moving along on a quiz to forget that and think that you're dealing with pH or POH or pKa or something of that nature. All right. So that takes care of that one. Coming back, we have question 6. And then after this question, when I wrap this one up, I will stop the recording so that we can put that up on YouTube and you can go back and review this. And then with the last couple of minutes, I will take any additional questions based on acid-base type work, okay? So question 6, this one probably out of the bunch would take up the most time. 25 milliliter solution of 0.1 molarity chlorous acid is titrated with 0.1 molarity NaOH. What is the pH of the chlorous acid after 5 milliliters of NaOH has been added, all right? So you do not need ice charts here because we're not finding the initial pH and we are not at the equivalence point, but you will have to have a little extra math instead of just Henderson-Hasselbalch, because you have to find how many moles there were initially, how many moles reacted, and so on. So let's take a look at how we should properly solve that one. All right, I'm just going to clear some space here for a second. All right, so for this, the first step, we want to find the NaOH used, and we're going to find the amount of acid. All right, so for the amount of NaOH that was used, because that's what's going to come off of the acid, let's find that value. It told us in the equation that we had 5 milliliters times the molarity given was 0.1. Right? So that'll tell me the moles of hydroxide that actually hit the solution. And that turns out to be 0.000500 moles. Or for those of you playing scientific notation at home, that is 5.00 times 10 to the -4th moles. Either of these values is appropriate depending on what your preference is. Okay, so that's the NaOH used. So then the next thing you move on to is you need to find the amount of the acid. So you have HClO2. Okay. Now for the initial amount, it's going to be 0.0250 liters because the question said there was 25 milliliters of it times 0.1 molarity. Okay, so that was the concentration. And that gives back 0.00250 moles. Or again, for those, because I did see quite a number of people trying to use scientific notation, 2.50 times 10 to the negative third. Okay. So the next step, once I have that, is let's find out how much of the chlorous ion, okay, because we have chlorous acid, how much of that conjugate base was actually created. Well, to do that, I need to take the initial amount of acid. And how much do I remove from it? It's the amount of sodium hydroxide that reacted. So it's going to be the 0.000500 number. Okay. And this is going to give back the amount of the chlorous acid that is still in solution. So if I solve for that, I get 0.00200, okay, moles. So this is going to be the HA that is left in solution for Henderson-Hasselbalch. This right here is the amount of HA that was reacted with sodium hydroxide. So I can view this as the chlorous ion A- in Henderson-Hasselbalch. Those are the values I have to work with. So now that was the only additional math. We're ready for Henderson-Hasselbalch at this point. So we come over and we set up the Henderson-Hasselbalch equation. This one, it gave the pKa directly and it asked for the pH. So we're finding the pH. We set that equal to the pKa, which is 1.95. And the values are going to be plus log of, okay, and it's going to be 0.000500. That's because that is A-. It's base over the acid when we're dealing with the acid. And then on the bottom, you're going to have 0.00200. So if you put that in your calculator, okay, and I do want to mention about putting it in the calculator in a second, you get 1.35 rounded as the pH. Okay, so I'd say maybe about a fourth of students got this question correct all the way. Some people, a lot of people knew to start this initial part, but there seems to be a lot of struggling with Henderson-Hasselbalch. Now, there's two things, one of which is probably just because you're not paying attention well enough. The other was kind of mystifying to me, and I'm not sure. So maybe somebody can help me out here. Okay. The first issue is that a lot of people were flipping these, not just in this question, but in all of the Henderson-Hasselbalchs. They're putting the value for HA at the top, and they're putting the value for A- at the bottom, and that's not correct. That's going to give you a different value. So there were quite a number of people here that flip the two of those, and when you do that, you're going to end up with a different value, and that's going to be incorrect. So usually if you had something like that, I saw that you did all the math prior to this and your only mistake was flipping the two, you at least got partial credit even though the answer was wrong. The other thing that I cannot figure out, there was at least, I want to say 4 or 5 students, they had everything set up on their work like this. They put the values in the correct spot and executed the Henderson-Hasselbalch equation, and they got a different value. And I don't, you'll see in the notes that I leave you, if you're one of these students, I'll say maybe you had a calculator error, but there was a lot of calculator errors going on here, if that was the case. So I'm not sure if people left a 0 out, if they put something in wrong, but these students would literally get to this point and then this value would be different. I think one of the common values I saw was like 2.3 something. And I just don't know where that came from. If accidentally, maybe this was, they put minus, but the way it's written, which is the only thing I can go off of, they still had these ratios correct here. So it was kind of bizarre to see all the work done correct. And then there was just that stopgap where people had the wrong answer. And it was the same wrong answer that kept coming up, but I haven't been able to figure it out yet. So, all right. With that, let me stop the recording, and I am going to then open it up to any questions that there may be for the last 10 minutes or so here. So let's stop recording.